So you see what happened. Sergio is not here. Oh, you are here. Okay. So I just yesterday realized that the last problem is actually connected to what I'm going to discuss today. So it was some kind of a miscalculation of time. I thought that we will cover this color and gluons. So what I want to say is the following. So you can give me your exercises as they are, but I will not grade the last exercise for time being. Okay, so that everybody will be on the same ground. Agree or not? Or everybody solved correctly? I don't know. So you will give me your exercises, and again, and I will tell to Giancarlo so that he will look, but he will not make any grade of this last exercise. And so this is, you will check them with this exercise number 4. And please distribute, and then you will give back this your present solutions. Because some of you knew things, it's unfair, right? Again, I'm trying to do that my lectures in such a way that it's enough to listen to the lecture to solve the exercises. So we started to discuss structure or quark structure of nucleons, or particle structure of nucleons. And to test the structure of nucleon, you need to have scattering with large enough transfer momentum. So to say, you need to have microscope which has wavelengths which is smaller than the size of nucleon. And the experiments, and those are experiments with deep and elastic scattering. Elastic when you have the same number of particles in initial and final state, you have just change of the momenta. Deep and elastic when you produce new particles, many particles, and Q squared is quite big. So we started to discuss features of this deep and elastic. I don't know. I have a problem. Maybe I should hide it somewhere. No. Let's see if it disappears from here.
Did you start recording?
Huh?
Did you start recording?
Yes. So what we are discussing is deep and elastic scattering. And we are discussing deep and elastic scattering of electrons, and that it was done historically. Then people also studied deep and elastic scattering of muons on nucleons and nuclei, and also neutrinos, but this was later. So we are discussing scattering of electron, and in the final state we have again electron, and X, which is large number of secondary particles. It's not just one nucleon. If we would put here nucleon, that would be elastic scattering. So it is characterized by big transfer momentum, Q squared, which is bigger or equal than 1 GeV squared. So with this energy, you can actually produce several pions, for example, Keon and certain also pions, several pions. So what people are measuring distributions of number of events on Q squared. Q squared. For different energies, total energies of in the system, in particular total energy of electron. And what they have observed is that distribution has quite big number of events with big Q squared. And that testifies that you have some small structure, so that the electric charge is not distributed uniformly inside the nucleon, but it is concentrated on some small object inside the nucleon. So this is one observation, and a second, which actually led to the picture, was Bjorken's scaling. So what is this? Let me explain what it is. In fact, it is convenient when the energy of electron is high enough, and of course energy should be bigger than 1 GeV, right, to have energy transfer, momentum transfer bigger than 1 GeV. We can actually consider the process in the system when you have both electron and nucleon moving fast. And the best is when you have both particles relativistic. We can write differential equation d sigma over dq squared, this is what is measured, in the form d sigma 0 over dq squared multiplied by f q, and in principle it also depends on the energy q squared and energy of nucleon. So what is this d sigma 0 over dq? This is cross-section if you would have point-like nucleon. So that is for point-like nucleon. And what is staying here, f, is structure function. Which actually describes deviation from point-like character of nucleon, and it describes the structure of nucleon. So it's also sometimes called form factor. I'm doing this more a bit simplified picture because people introduce different or several structure functions or form factors with different Lorentz properties. But for me, it's just to give a scheme. It's enough to have this one. So let me repeat again and write diagram for this scattering. We have electron in final state with momenta Pe and Pe prime. Then we have photon, which interacts with nucleon, and Pn is momentum of nucleon, and then we have a final state of hadrons, I denote by X. So this is photon, and the transfer momentum is for momentum of gamma, which is propagated here, and it is given by P minus P prime. So this is transfer momentum, or for momentum of virtual gamma. So gamma is virtual here. So let us focus on this part of the diagram, which describes the scattering of interaction of virtual photon with nucleon, with production of the system of hadrons in the final state. So in general, the structure function which describes actually interaction in this point is the function of two variables, q, this is momentum of gamma, and Pn, right? What has been observed in the experiment is that actually dependence of structure function on q or q squared and Pn is not like arbitrary, but these two variables q and Pn, enter function f in the combination xb minus q square 2 q Pn. What does it mean? This means that if you increase Pn by factor a and increase q by factor a, x will be the same, right? Because you have q also here. So it scales like q over p. And so if you change by the same factor, q and p, you will get the same x. And structure function depends on this ratio. It's not independent q and pn, but this ratio. Which means that, that if you change p by some amount, so you go to higher energies, for instance, and then you change q by the same amount, then the structure function will be the same. Okay? So it depends on these two variables only in this combination. At least if scaling is exact. Scaling means that you have this variable, and by the scaling q and p, you do not change. Okay? Questions?
Is there any way to derive the structure function directly from quantum electrodynamics?
So, you see, actually there are even differential questions. Parelli-Parisi give you these wave functions. If you fix them at some levels, say initial conditions, then you have differential questions which tells you how these functions look like at different q square and different momenta. But then to have this kind of initial condition for these structure functions, you either need to go to very low energy, so to see what's going on with proton, and this is non-perturbative physics, so you cannot do this. Or you can measure them at some high energies, and at least at some some energy, and then you know how that functions change when you change other variables.
Okay, I guess so. You can find the differential equation and then search for initial conditions. That's the idea.
Yeah, so that you can do. Okay. So if you go to log frame, where momentum of nucleon is 0, so that Pn is the mass of a nucleon, and here is 0, then this x variable, which is called Bjorken variable, it is given by q square, and here is two masses, and this is nu, this is notation people are using, and nu is transfer energy. You can see these expressions. Transfer energy from so transfer energy by electron. Okay, it's clear that you just take here the first component, zero component, and then this will be difference of energies. So this is how this variable appears. So again, let me remind exact scaling, because I was saying about this of the Parelli-Parisi question. Exact scaling means that no need even to solve any differential equation, because if you measure your structure function at certain energy, p, or certain momentum of a nucleon, and you want to know what is this structure function at other different energies, you just do rescaling. So if you by the same amount, so distributions will look like the same, and you just rescale q square. Okay? So nothing to solve even. Clear? again, so the structure function is the function of q squared to q pn. And so knowing the structure at one value of pn, you can find this for any other values of pn by just doing rescaling of q squared. If you want to have 10 times bigger energy, then you will get the same distribution, but for 10 times bigger q. Okay? Now, what's interesting that this scaling phenomena can be explained by the picture, this Parton picture, that nucleons are the states which are composed of point-like objects on which scattering occurs independently. And so now I will show you this. So let me repeat this. Scaling. Can be explained by Parton picture. At the following conditions. So now let me consider these conditions. First, is that the partons should be considered as free particles. This means that nucleon or nucleon at high energies should be considered as the flux of free partons. Which looks quite strange, right? So we deal with strongly interacting particle, and nucleons themselves have strong interactions. And this is a very compact object. And you have inside some objects which are, say, electrically charged. And you need to keep them within this radius 10 to the minus 13 centimeters. And it turns out that at high energies, it looks like you have proton as a just free flux of partons. So that if you have nucleon, you can show it or consider or treat them as just flux of partons. And at high energies, you can consider almost like a parallel flux of partons, although there are some corrections if you consider some transverse motion, but we will neglect for time being. So let us denote as Kp is momentum of parton. And then you can introduce variable x so that Kp is the x momentum of nucleon. Then x is fraction of total momentum of nucleon carried by a given parton. So the different partons inside the nucleon, they have different x. But of course, the sum over x over partons should give 1 if you count all the partons. Okay? So this x can be written as k parton over momentum of nucleon. And of course x changes from 0 to 1. So you can also treat, okay, so that's changes from 0 to 1. And 1 means that at certain configuration it might happen that all the momentum of a given nucleon is concentrated on a single parton, which is not excluded. And you also may have some partons with very small x, so it's very soft, carry a very small amount of energy for momentum. Okay? Second, that scattering of electrons on individual partons proceeds independently or incoherently. Incoherent. And this is realized if 1 over q, or wavelengths, with which you probe your nucleon, is smaller, much smaller than distance between partons. That's why we need to have high energies. Okay? So that what happens in this case is that you have electron which meets the flux of partons which correspond to nucleon and scatters on one of these partons. Another just proceed without any effect. Effect will be later. And so you need to consider scattering of electron on all the partons and then sum up cross section. Right? So that d sigma nucleon over dq squared, this is what we studying, equals sum over partons of these individual cross sections, elementary cross sections on partons. Dq squared. Okay? So for time being, this is assumption, and I will show you that this leads to scaling phenomena, which actually confirms all this picture. We can substitute summation by integration as usually. and introduce continuous variable x. So we can actually describe property of a given parton by x, fraction of momentum. But it also may have some other quantum numbers, may have quantum numbers like electric charge and other things, so we need to take into account all these. So let's substitute summation by integration. So that the given parton is characterized by x, by fraction of total momentum, it cares. It may have electric charge, it has electric charge, and different partons may have different electric charges, and may have some other properties. Since we are discussing here electromagnetic interactions, so we are more interested in electric charge of the parton. So what we are introducing n, number density of partons of a given type with a given x. This is number density. And then contribution of partons with a given x to cross-section on nucleon is just given by d nucleon over dq squared equals d sigma parton over dq squared multiplied by nx. And again, if you have several different types of partons, then we need to sum over other characteristics. So for instance, if we have partons with different electric charges, then we need to introduce this number density for each of these electric charges and then make summation on electric types of the partons. But I, for simplicity, consider just a single type of the partons. The fourth point is that partons are point-like objects. So they have no substructure, and therefore d sigma parton over dq square is d sigma 0. This I denote scattering on a point-like object over dq square. And therefore it just can be written as d sigma 0 over dq square multiplied by nx. And now remember our parameterization in the beginning of the cross-section. And then clearly this n is nothing but structure function in this framework. Okay? So this is structure function. Our f is, let me put proportionality, is nx. Since this is scattering on a point-like object. Now let us elaborate more on x. And this is fifth point. That scattering on individual partons is elastic. So that it's already written here, shown here. So let me write this in more details. So what happens is the electron scatters on individual parton with momentum k p, and final momentum of parton is k p prime, and here we have q, momentum transfer. Okay, so this is how the scattering on individual partons occur. So let us write energy momentum conservation here in this vertex, and what we have is Kp plus Q equals Kp prime. Right? So I'm writing energy momentum conservation for this vertex. These are 4 momenta. And Q here is virtual, so that it's not on the mass shell, so I can satisfy energy momentum conservation in this form. So let me square this expression, and what I will get is Kp squared plus 2Kp Q plus Q squared equals Kp prime squared. Right? So this is the mass of parton squared. This is also mass of the parton squared. And I consider this process elastic, so that the same parton is in final state of the same mass as in initial. These two guys cancel. And what I will do next is I have here for momentum of parton, and remember we introduced x variable, so that Kp equals x and momentum of nucleon. Considering that k is moving along this p, so it's parallel, not considering any transverse motion, which can be done to a good approximation when you are at high energies. But in any case, the partons inside the nucleon can still have some orthogonal momentum, but it is not bigger than, say, inverse of the size of the nucleon. Okay. Now, then, using this equation, I immediately write that x, when I insert this, equals minus q squared over 2 Pn times q. Right? So what is left after this is this, and I inserted here k p, and so I get that expression for x. And remember what we have written, that in this framework structure function is just given by nx, and now we can write this as n minus q squared 2 Pnq. So that is nothing but previously introduced Bjorken variable. And so in this way we have proven that in fact the structure function is the function of combination of this type. So in this picture, xb, Bjorken variable, which we have introduced just on general ground, some variable in structure function, has a physical meaning in this parton description, and it is nothing but the fraction of momentum of nucleon which parton which is carried, but not parton, which is carried by parton on which scattering occurred. So you have scattering with a given q squared and for a given momentum p. Then x, this Bjorken variable, which is constructed out of this Lorentz invariant, tells you what is momentum of parton on which scattering occurred. So once you know q square. You measure it in scattering. Once you know what is momentum of nucleon, you know this, and you know that you have a scattering with a given q square, then you know what is x fraction of parton on which scattering occur. So q square determines the momentum of parton on which scattering occur. Okay? Now, in experiment, you can measure these structure functions. This is what has, okay, so maybe questions. So what we have proven that scaling can be explained if you assume that your nuclei or nucleons are states composed out of point-like objects which are independent and scattering on which are free. So you have not, in first approximation, any interaction between them. So it's just flux of these partons. And then scattering of electron occurs on individual partons incoherently. And then result of scattering is given by the sum over these partons. If you have a fixed q square, then scattering occurs on the partons with certain value of x. Momentum fraction.
How is this free particles flux assumption valid? If we know now that inside nucleons they are actively interacting between them.
Yeah, which means that for this process of scattering, the fact that they are interacting between each other is not important. And that has explanation. So we will go to asymptotic freedom a bit later. So we deal here with scattering at high energy, some large q square. So what we will see later, that actually strong interactions become not strong, they become weaker and weaker when you go to high q square at momentum. And that explains this picture. Okay, so I would advise to repeat all these arguments and to check if you have the right understanding. So what I have proven for you is that the scaling actually can be explained in the picture when you have these free partons and interactions with free partons. You may ask questions, so maybe there's some other description, right, which leads also to scaling. So you may try, but this is what has been eventually checked in many different ways and confirmed. Now let me say a few words about the properties of structure functions. They were measured, right? So just studying a scattering and measuring distributions over q square, number of events or cross sections, you can measure these structure functions. And typical form of these structure functions is the following: x, and here is x multiplied by nx. So this is what usually people show. So you not just nx density, but also multiply by x, and it has typically dependence like that. Because maximal is 1, and this is 0. So you have so here 0 probability, so very small probability that all the momentum is concentrated on a single pattern. So this means that nx itself is divergent. But in most of the cross sections you compute, there's actually such a combination appear. You will have an exercise to check this for production of W boson. You have some this exercise in this problem. Now the present day interpretation of this is the following, that actually you have different types of partons inside the nuclei, you have so-called partons which correspond to valence quarks. So still, I have not discussed that what are these partons. Eventually, at least part of the partons was identified with quarks. And it was checked that in fact these partons have electric charges as the charges of quarks and the same other quantum numbers. So this has the following interpretation. Maybe I should sit a little bit like that. Sorry. So that's like this. Something like that. So eventually, detailed studies show that there are several components here contributing to this distribution, and one is which corresponds to valence quarks. So these are quarks which carry quantum numbers of nucleons. For instance, in the case of proton, these are U quark and D quark, right? Now, again, let me repeat, you can treat this distribution as number density, but also the probability that you find in a given nucleon in a given moment of time quark with a given x. Okay? So, these are so-called valence quarks, but here what you have is quark antiquark C of quark antiquark pairs. And saying a bit in advance, this is produced as you have valence quarks, and you also emit gluons, and these gluons produce quark antiquark pairs. So these are soft components in this distribution. And of course you have also gluons, which you do not probe by electromagnetic interactions. They are neutral, but they carry part of the momentum of the nucleon. So what you would expect is that if you measure using electromagnetic interactions these distributions of quarks, and then make integration over x, that would give you total momentum carried by a given type of the quarks, then you sum up things and you will not get one. So which means that there is some component inside the nucleon which has no electromagnetic interactions. And that was later identified with gluons. Okay? So we'll come to this a little bit later when I introduce gluons to have more detailed description. Well, actually, this is, since you have 3 valence quarks, this is close to 1/3, so that's kind of nice correspondence. So next topic is gluons and strong interactions and discovery of gluons. So, and I first start with color, introduction of color. So the color was introduced in an attempt to explain the problem with Pauli principle for sum of hadrons. And in particular, what has been observed, has been found, is delta plus plus particle. So actually, you saw this in, not because this is, that corresponds to spin 3/2. This is baryon. And its quark content is U, 3 U quarks. So each of you quarks has a charge to third, therefore the sum is 2. So total spin is 3 over 2. And for all lowest states, L is 0. And then the problem is that we have 3 quarks of the same type, the same state, in the same state. So, which actually is not possible according to Pauli principle. Even if you introduce, and I don't want to, so you can make some analysis, you can wonder, okay, maybe 2 quarks have kind of opposite orientation and you introduce internal angular momentum to have 3 half, but still 2 quarks will be in the same state. So another particle which creates the problem is omega minus, which is the system of 3D quarks. And again, the same problem, you have 3D quarks in the same state. So because you need to have, each of them has spin 1/2, you need to have 3 half, they should be oriented in the same way. So that's contradiction to Pauli principle. So quantum mechanically you have your nucleon, so this is your baryon, and then you have the same wave functions of 3 quarks sitting in the same volume and have the same properties, but you need to have some asymmetry to satisfy Pauli principle. Solutions to this problem has been proposed by Greenberg, Hunt, and Nambu. And independently by Bogolyubov, Tavkhelidze, and Struminsky in Dubna. So this is not well-known paper actually, but as usually, so something which is produced in Soviet Union and Russia is not well known, and so that mostly people are citing Greenberg, Hunt, and Nambu. And the idea is that actually quarks have additional degree of freedom, which distinguish 3D quarks inside this omega minus or 3U quarks inside delta plus plus. And this degree of freedom is called color. And the idea is that all the quarks have actually represented in 3 different colors. So actually you have not a single U quark, but there are 3 U quarks which differ by color. Sometimes it's just 1, 2, 3. Sometimes people are associating this with, say, red, yellow, blue. Maybe someone likes something else. And therefore, the wave function of delta can be written as wave function of u in the following way. Let me write and then I explain. J and u k. And then antisymmetric tensor epsilon a j k. So that these a, j, k are different. And you make a summation over a, j, k.
So in this paper, the Greenberg and Nambu paper, did they use the term color?
Yeah. I don't remember actually who was first to introduce this terminology.
It has to be American because there is American style of color, not the British style.
Well, Nambu was in US, so I think all the US. So this is antisymmetric tensor. So which actually implies that I, J, and K should be three different indices. They should be different.
Should there be a normalization factor? Should there be a normalization factor?
Yeah, so I mean this. I can write here proportionality. Now, in fact, Nambu already mentioned that color may be just not for classification, but it may have some kind of dynamical feature. And it may be the coupling constant of some new interactions, strong interactions. So dynamical characteristic. Well, actually, this gives you some hint that that the group, symmetry group, could be SU3 because this is antisymmetric tensor is kind of the constant of this SU3, structure constant of this SU3 group. So, after introduction of color, one could say that hadrons, which we see, are colorless combinations of quarks. So, something which is invariant under symmetry transformation. This is one of the combinations which is invariant under, and I will say, SU3 group transformations. So another combination is when you have UI, Uj, and you sum. So you sum over I. So this is also color invariant combination. And then the statement is that observed hadrons are those who have zero color. And this actually explains why representation 6 of hadrons doesn't exist, because representation 6 comes from QQ combination of quarks, and this is not colorless. So immediately after introduction of current, color can say why these 6 pairs do not exist, because they are not colorless. So next step is construction of gauge theory of color. And that has been done by Fritsch, Gell-Mann, and Leutwiler in '71. Gell-Mann and Leutwiler. What they say is that quarks form color triplets. Say U quark, U triplet is U red, U yellow, U blue. And they are transforming under fundamental representations of SU3. So this is different SU3, right? So we discussed before flavor SU3, and fundamental representation of, say, U, D, and S quarks So here you have for each type of the quarks these triplets. Again, the sense of this transformation is the following. Eventually we create some theory, some Lagrangian, which should be invariant with respect to these SU3 transformations. So they are transformed under SU3, and let me put here color to distinguish its flavor. Now we know how this gauge theory, so theory which is gauge invariant, can be constructed. So once you know that this is SU3, then you know how to construct gauge invariant theory. Let me just give you a sketch of what happens. You introduce gauge bosons in the same way as you have gauge boson, which is photon, right? So you have kind of here analogy of electromagnetic interaction. So you introduce gauge boson, and gauge bosons to construct SU3 invariant Lagrangian should be in a joint representation. Representation of SU3. So this is how we can construct invariant Hamiltonian. So actually you have this exercise, right? You constructed an invariant Hamiltonian, and you have doublets of nucleons and triplet of pions. So this is again the same idea, how to construct invariant things. But this was global symmetry, so here is local symmetry. So you have 3 pions, right? And you construct. So here you need to have a joint representation of SU3, and that contains 8 bosons, which are called gluons. So what these gluons are doing, they change the color of quark. So if you have color, a quark with color I, then emitting gluon, the quark changes the color and it becomes QJ, and therefore each gluon carries double color. So this is gluon, and it has index J and I, and these indices run from 1 to 3, right? So I, J, 1, 2, 3, and Lagrangian of interaction, Hamiltonian of interaction is the same essentially as in the case of electromagnetic interactions. It's given by coupling constant, and then Qj, gamma mu, for alpha we decided to put Qi, and I put gluon, which is Ji, and it has index mu, because so alpha, because this is vector pi. So gluons are analogies of photons.
If we have gluons represented by GH, GIJ, and IJ run from 1 to 3, then
trace, you need to require that trace is 0. So therefore one combination go out. This is why I'm saying this 8. So you have 3 times 3. Okay. And within SU3 you have these 2 structure constants, which are delta ij, which actually corresponds to mesons, and epsilon ijk, with which you can construct invariants of the group. So this is how these mesons and baryons appear. Okay. So for my consideration, it's enough just to introduce this type of interactions of gluons with quarks. So let me say a few words about dynamical features of these interactions. So this gauge theory is what is called chromodynamics. Gauge theory, SU3 of color is quantum chromodynamics. So let me give you some elements of dynamics. So we have gluons, right? Which are gauge bosons. Spin 1. And massless. So the mass of gluon is 0, so the symmetry is not broken. The big difference from electrodynamics, difference from photons, is that there are self-interactions of gluons. So why there is no self-interactions of photons, at least at a fundamental level? It has no charge, right? So photon interacts with everything which has charge. So gluons interact with everything which has color. And since gluons themselves have color, therefore they should interact within themselves. And in fact, there are two types of interactions. Let me see this probably.
So that means that there is 24 different gluons.
Why?
One for each
8?
color.
What? Sorry?
One for each color.
No, there are 8. So we decided that we have that should be in adjoint representation, and it is given by gluon ij, and you have 3 times 3 minus 1 because you have a irreducible representation. Why? 24.
But if gluons have colors, how to know which of these 8 have each color?
So you have 8 gluons. What do you mean? How?
You said that gluons have colors.
So there are, say, gluon 1, 2, gluon 1, 3, gluon 2, 1.
Yeah.
So there are 8.
What is the color of each of these gluons? What is?
So it's double color.
How the double color?
So what? Double color.
Okay.
So you have gluon which is red-blue, for instance,
Okay.
if you want, or yellow-blue.
And the gluon that is red-blue is different from the one that is blue-red.
Sorry?
The gluon that is red-blue is different from that of blue-red.
Yeah. So they're different particles. They have different color.
Why is it double color? Why is it double color? Why is it double color?
Because we have 2 indices here.
Ah, okay.
Well, if it is not double colored, then it cannot.
We cannot construct them invariant combinations. Like again, think about your pines. You can also write 3 pines in terms of matrix, remember, with 2 indices. So if you want that pines on pi 0, pi plus, pi minus are double isospin particles with double isospin index, right? The same way.
If you want a single color, then they cannot change the color of a quark.
They cannot change the color. You will not have a conservation of unless you introduce coupling of 2 gluons in the same place. But this is not the way how we're constructing. So if you want to construct a normalizable gauge invariant Lagrangian, then you need to introduce a joint representation. Again, this is how gauge invariant theories are constructed. So in the beginning it was of course just idea, but then it was checked. I said you have these 8 gluons. So I'm saying that there are self-interactions of gluons. And in particular, you have interactions of 3 gluons in one point. So you can construct an invariant combination and you have 3 gluons and 4 gluons. We have this new. Actually, the same story is for weak interactions when we have W bosons, but this is SU2. You will see later. Again, the same principle, and again, you need to introduce couplings between photon and W bosons. So W bosons, remember, we discussed a little bit. So you can couple them with charged currents. Since they are charged, then they should interact with photon, right? So not exotic situation. So we have coupling of 3 bosons. And we have coupling of 4 bosons also. Now, existence of these new interactions leads to very important consequences. Now let me discuss a little bit effective coupling constant. So what we introduce in our Lagrangian is suppose lowest order coupling, right? For instance, in the case of electromagnetic interactions, we have coupling of photon and electron and electron. But of course, using rules of QFT, you need to take into account corrections. For instance, of this type, plus corrections of this type. And I think at some point in the QED course you will discuss these things. And what you observe in the experiment is not just this lowest first order, but what we observe is a summation of all these kind of the processes with corrections. So your physical electric charge is, the sum is given by the sum of all these diagrams. It's just what you see here is one loop diagram. You may also write like here, like this. But actually you need to make a summation of all orders of perturbation theory. So this is, once you start to do perturbation theory, you must do this. And you need to make this summation to get physical quantities. So here are photons, right? There's gamma here. So what is important is that if Q is momentum of a photon, these diagrams or these contributions will depend on Q squared. So these contributions and the rest will depend on Q, or Q squared. Okay? So we'll do these computations and we'll then understand what's going on. So what you can do is the following. You can fix your electric charge, physical quantity, at some scale. So like you are measuring electromagnetic couplings at very low energies. Okay? You fix this, but then due to this dependence, your effective coupling constant will change with Q. What is interesting in the case of electromagnetic interactions, when you go to higher and higher Q, the coupling increases. It's logarithmic increase, but it increases. So it increases, and at some point it has a pole, which is called Landau pole. It becomes infinite.
QED.
In QED, right. So this type of the diagrams give increase of coupling constant with Q. The presence of these new additional interactions in QCD changes this behavior, and the coupling decreases on the contrary. So in the case of QCD, you need toy diagrams of the following type. So apart from this also exists, but you need to add diagrams of the type of these are 3 gluons interactions, and also coupling like this, where at this point you have 4 gluons interaction, and they have opposite sign with respect to the loops produced by fermions, and therefore what happens is that effective coupling constant alpha QCD decreases with Q. So and you know that that Gross-Wilczek and Politzer got a Nobel Prize for this observation. So that the effective coupling constant in QCD it decreases with Q squared. So what is interesting that actually the first computations have been done by Kriplovich in Soviet Union. He computed these diagrams correctly, got correct sign. I just didn't do anything else. I just there's a preprint, I think published eventually, without discussing physical consequences. So you see, it's not only enough just to make computations and got correct sign and everything, but also to extract what is the physical meaning of this result. And physical meaning is striking. So this is dependence of alpha QCD on Q square, on Q, I put here Q. And it depends like inverse of logarithm. So dependence is alpha C equals log, and here Q square over lambda square QCD. And from the experiment, this value is around, lambda is around 300 MeVs. So what happens is that the coupling essentially becomes infinite. It diverges at Q equals lambda QCD, and it decreases with Q. And in fact, nowadays the very precise measurements of this behavior, so points like this, up to very big actually Q squared or Q. And for instance, at Q equals to mass of Z boson, where we have very precise measurements, alpha QCD is close to 0.11. So at low energies it is big, it's infinite. But at higher energies it becomes quite small. And there's a lot of consequences of this behavior. So this decrease of the coupling constant is called asymptotic freedom. So alpha go to QCD to 0 when Q increases. And it means that in asymptotics, strong interactions become very weak, like disappear. So this is in the basis of grand unification. Idea is that electromagnetic coupling constant increases with Q squared, although it is small at low scales. So behavior of electromagnetic coupling constant is like this. It increases. And at some big Q, they can be of the same order. So they can be related. It's not equal, but related, and that allows you to unify strong and electromagnetic interactions, and also weak interactions can be unified. So weak interactions have different behavior. So it's like this, and it happens that in some point these dependencies can meet each other. So you have asymptotic freedom, and asymptotic freedom tells us that coupling, strong interactions, couplings of quarks, strong interactions of quarks become smaller and smaller at higher energy, high Q squared, and therefore, so that explains deep inelastic scattering results. So we can at high energies treat in the first approximation quarks as free particles.
Also means that we cannot have an isolated quark.
We have not?
We cannot have an isolated quark.
Yes, so this is, we are still here, right? So that explains scaling. Explains the results of deep inelastic scattering. So on the other hand, when you go to this range, you have divergency of the coupling, so you have a regime of very strong interactions. And the idea is, in connection with this increase, you may have confinement of quarks. Confinement of quarks. So this is actually what keeps quarks within inside the nuclei and nucleons. Well, there is a kind of naive analogy of this behavior. Like if you have rubber, so you have two bodies, connected by rubber, and if they are at small distances, and small distances means high Q square, right? So you have weak interactions between them. So rubber is not, there's not big tension, so that they can be considered as almost free. However, you should start to separate them, and separation means small q, right? So then the rubber produces the tension. Okay, so you cannot remove further. So that's kind of very naive picture. However, it gives some idea what's going on. So quarks, when the distance between is small, the forces, strong interaction forces, are weak. And so if you are treating some interactions at very small scales, you can have a very small effect of strong interactions. While if you have, you start to separate two quarks. So what's going on that the interactions become stronger and stronger, and so you have kind of a flux which connects these two quarks, and at some point the flux can be broken, and so you produce additional mesons. So this is how it works. Let me repeat it again. So you have forces like electromagnetic forces, but now we have here these QCD forces. So if two quarks are close, then there is no big tension between them, but if you separate, so there's a big high tension, and then at some point you can break this, and what will happen, you will produce quark-anti-quark pair, and so instead of having just three quarks, you will have the system of two mesons. Okay, so this increase of tension is what happens when you increase the distance. So at some point you will produce, the tension is so big that you produce another quark-anti-quark pair and then form two hadrons. So this is why you do not see three quarks. Questions? So remember again, so this is important, and then it's important also to solve the problems. So if you have strong interactions, if you have quarks and they are at small distances, the strong interactions are weak. So they become strong when you start to separate them, and you have some interactions which are kind of long range, relatively long range interactions. So it's not accidental that this is QCD, lambda QCD is something like 300 MeVs. This ensures that you have these composite structures of the size 10 to the minus 13 centimeters in particular.
So confinement is broken at very, very high energies?
Sorry?
Confinement is broken at very high energies?
Yeah, which means that how can you say confinement? When you go to higher and higher energy, then the distance becomes smaller than the size of nuclei or nucleon, right? So you see, in this regime, you have this size of nucleon, but quarks are somewhere here. And you do not see three quarks still. And you cannot say confinement is broken. So confinement still exists. The point is that you have two small distances. You do not probe big distances. So when you start to separate these two quarks, then the distance increases, then forces become big.
That lambda QCD, how is it derived from the theory? Or
So what you are doing computation of these corrections to the lowest order.
of the slopes from that?
Yeah, yeah. And then you need to kind of to get this lambda at least at one scale, and then you know what is behavior at different scale. Because a priori you don't know what is this coupling. You can do this if you say, I want to have gut scale, gut theory, transunification theory, then I can predict what should be alpha KCD at low scale. So what is happening? You measure this coupling at least at one scale, and then you fix what is this lambda KCD. Then you know all the behavior. Okay. So now I will discuss, and this what I will focus on is how to test all these things. And the first thing is how I can prove existence of color and how we discovered gluons. I'll just start to say a few words and then we will continue next lecture. So actually this information is enough to solve the problem, right, with this tau left decay. So who knows how we really counted colors experimentally, how we confirmed the existence of color? What was the experimental test? And gluons. Experimental tests. Remember, who knows?
Maybe branching radius?
Sorry?
Branching radius? Which I think that it decays to many.
Yeah, this is one of the ways, yeah. But so we discussed, so you have this exercise with tau, right? But that already was confirmed before tau. Yeah, to get correct expression for tau decay, you need to take into account that quarks are present in three colors. Now, one of the important things which people use to prove existence of color is E plus and minus annihilation. Into hadrons. So measurements of total cross-section. So this is the process when you have sigma. What measured is sigma E plus E minus equal to hadrons. So you have collision of E plus, E minus. And in the final state you have some number of hadrons. And I will make just one comment and then we will continue next time. So this process, according to our picture of strong interactions, can be considered in two phases. What you have is that you collide E plus, E minus, and at small distances, smaller than 10 to the minus 13 centimeter, much smaller, 10 to the minus 14, you can treat this as production of free quarks. Right? So you produce quarks. quark-antiquark pair. And then when you move quark-antiquarks one from each other, so the interaction becomes strong, and then there's a second phase. So the first phase is E plus, E minus, produces quark-antiquark pair, and then when you go to bigger and bigger distances, strong interaction becomes stronger, and this quark-antiquark pairs is converted to hadrons. So you have two phases. One is short range, phase when the distance between quarks is much smaller than 1 over lambda QCD. And here you can just treat production of free quarks, and the diagram is Q bar, sorry, E plus E minus. So you have E plus E minus, annihilation through photon, and that produces quark-antiquark pair. You can treat it as a kind of production of free quarks. And then long-range interactions, strong interactions become important, and this is what we call this hadronization of this, or fragmentation of quarks into hadrons. So we'll continue on Monday. Questions? So is this clear? So when you have this is first phase, and then they start to move from each other, and then they fragment into hadrons. So this is short range, and then they fragment by also exchanging by gluons. So they fragment to produce hadrons, colorless objects.
At lower energy, you can use perturbation theory, or do you use instead?
At low energies, no, at low energies we cannot use that becomes strongly interacting coupling theory. So there are some non-perturbative methods, or
in the lattice, right?
lattice for this, or also lattice you can use.
So, that's QCD for lower
Yeah.
energy?
Yeah.
Okay.
Can we estimate lambda QCD by comparing the force of the strong force with the electromagnetic force inside a certain nucleon?
No, but you need to still have some measurement of your alpha coupling constant. Just if you can do this relatively to electromagnetic interactions, but you need to measure somewhere.
Yeah.
Now, in the case of nucleon, you have already very strong interactions. It's difficult to extract information from this. But if you go to higher energies, yes, you can just directly measure this coupling, because you can use perturbation theory at high energies.
I have alpha of electromagnetic interaction.
Yeah.
I have the radius of a nucleon.
No, but if you are inside the nucleon, then it's strong interactions are strong. Well, you can say that I can measure lambda by just measuring the size of nucleon, if you want.
Yes.
Right? So it's of the same order, because this is the distance at which strong interactions become strong, roughly speaking. So it's